Hello, my name is Mark Cairnie, and I am a PhD student at the Center for Power Electronic Systems at Virginia Tech, where I'm advised by Dr. Christina DiMarino. Today I'll be talking about prototyping and evaluation of a high-speed 10 kV SiC MOSFET power modules with high scalability and system integration solutions. Today I'll be focusing specifically on the system integration solutions and the optimization and design of the high-density interface between the module and the integrated bus bar. This project's been carried out in collaboration with the National Renewable Energy Lab and Wolfspeed. High voltage, high speed silicon carbide MOSFETs bring new possibilities for smaller, more efficient, and more reliable power electronic systems in a wide range of fields. In order to fully take advantage of these new capabilities SiC MOSFETs offer, new, innovative, high-density packages must be developed to minimize the parasitics so that we can maximize the switching speeds and in turn minimize the losses. Shown on the right is our current version of a 10 kV silicon carbide MOSFET power module. The module is a half bridge with 3 devices in parallel per switch, so 6 devices total. The module achieves a power density figure of 18 watts per millimeter squared, which allows us to achieve a parasitic power loop inductance of only 4 nanohenries. Now, this compact module design is made possible by avoiding the clearance and creepage requirements between the terminals of the module. So shown here is a cross-section of the module which shows how careful design has removed any in-air path between the terminals. So the high voltage terminals are completely isolated from one another. They're sealed beneath the module housing by the encapsulant and above the module housing by the PCB integrated bus bar. So this voids the need for standard creepage and clearance requirement and allows us to reduce the terminal-to-terminal spacing from the IEC 60664 recommended value of 40 millimeters down to only 11 millimeters, which gives us an effective 73% reduction in size. However, with this drastic reduction in the terminal-to-terminal spacing comes increased electric field strength around the terminals, and this needs to be carefully managed to allow for a breakdown-free and partial discharge-free operation of the module. So shown in the top left is a 2D CAD model of the field grading geometry inside the PCB integrated bus bar. And this geometry is carefully designed using an FEA-driven numerical optimization technique to ensure the electric fields in these regions are kept at a manageable level. Using a numerical optimization technique for this problem allows us to optimize the design for a large number of design variables and a high degree of complexity, all while reducing the design time. The geometric structure to be optimized, such as that field grading geometry from the previous slide, is first parameterized in terms of its design variables. From this parametric model, we can extract a 2D boundary value problem where the boundary conditions of the problem form the optimization variables. Now, this workflow has been implemented in MATLAB, where we're able to use a variety of off-the-shelf and custom optimization algorithms to go ahead and optimize the design. So here's an example of a cross-section that was designed using both a manual optimization process in ANSYS Maxwell and a numerical optimization technique using our own custom FEA optimization tool in MATLAB. Now, the version 1 of the module interface took roughly 8 weeks to design, and during tests it demonstrated a partial discharge inception voltage of about 8.5 kV RMS under a 60 Hz sinusoidal excitation. Now, when the interface was redesigned in version 2 with the numerical optimization tool, it took roughly a week to design due to the increased speed of the tool. And during tests, it demonstrated a partial discharge inception voltage of 11.6 kV RMS under the same excitation. Now, not only did the numerical optimization tool increase the PDIV, but it also did so with a decreased terminal-to-terminal spacing due to a higher pin count in this version of the interface. Here's an example of how the performance of that module to bus bar interface is experimentally validated. On the bottom left is a photo of the partial discharge dummy module, which is a module constructed to be electrostatically equivalent to a functional module, but with no devices in it. Now, the module is fixed to a bus bar and excited under a 60 Hz sinusoidal excitation. Under this citation, the significant partial discharge does not occur until 11.6 kV RMS, as shown in the PRPD plot in the bottom right. Now this PDIV allows for a safe, partial discharge-free operation up to the device limit of 10 kV. Next steps for this project include integrating the gate drivers for both the high side device and the low side devices into the bus bar PCB, as well as full dynamic characterization of the module and eventual converter integration. Thank you for your attention.